Welcome back to Applied Physics. In this video, I want to talk about friction. We are all familiar with the basic concepts of friction. We know that when we push an object, it is going to stop moving eventually. Right? I'm going to immediately get my head out of the way. I apologize, this is a little bit bright, but let's look at this nice simulation of us, a crash test dummy, applying a force that I can control by this slider down here onto a crate which has lots of friction. As I push, it starts moving, and when I let go, it stops. If I get rid of friction, which they simulate in this by drawing it with ice, and I start pushing, when I let go, the box just keeps going, and it will not stop, it will not slow down, it just stays at the same speed. If I put the speed up here, you can see that the speed is not changing. It is not slowing down in any way, shape, or form. All right. That's the kind of ideas that you are already familiar with. You probably are also familiar with the fact that different materials have different amounts of friction. If you are walking on rubber mats, there's generally a relatively high amount of friction between your feet and the floor. If you're walking on linoleum covered in puddles, there's generally less friction. And if you're trying to walk on a sheet of ice and you're not lucky, then much like the crate here, there is no friction at all. So if I get back to my lecture notes, let's get my head out of the way so I can start writing some stuff down. So what do we know? We know that friction is a force. We will write the force of friction as big F subscript little f. That'll generally be a vector, so we can put a nice vector hat on it. We know that friction occurs between two materials. And related to that, different materials have different amounts of friction. If we zoom in, if I go back over to the entirely too bright screen, and we take a look here at an incredibly close view of a chemistry textbook and a physics textbook sitting on top of each other. When you zoom in far enough, you can see that the chemistry textbook and the physics textbook are made of individual molecules. And in this particular case, our physics textbook is going to have a nice glossy cover, so the molecules are pretty nicely organized and the surface is relatively smooth. Right? If you've ever bought a brand new glossy covered textbook, you know how smooth they can be. The chemistry textbook, on the other hand, is very rough. So this might represent something like a textbook that is bound with a cloth cover. So there is going to be some irregularities to the edge of it. And if you zoom in far enough, you can see these irregularities appear in the molecular structure. I say you can see, but let's be honest, it's prohibitively expensive to zoom in far enough to actually see the molecular structure of these things, but we can envision what it might look like. Right? But if I grab this chemistry textbook and I start moving it back and forth, in the zoom in you can see I'm moving it quite a bit, in the close-up a little bit less so, but eventually these molecules try to move against each other, and behind my head you can see that there is a thermometer. As I rub these books together, the physics textbook is going to warm up. Sorry about that. Oh, I thought I muted those sounds. Sorry about that. There we go. There is no reason to hear all of that. All right, but if I rub these together, they're going to heat up. And if I rub them together enough, what you're going to start to see if I can get it to work without being too annoying here. But you're going to start to see some of the molecules, the jagged edge of the chemistry textbook, are going to start breaking away. They have enough energy that they start to scatter. And if you do that long enough, you can get that book to be smoothed down. This is a process that we know in the woodworking industry as sanding. There's one other thing that you can think about with that sort of a picture, although this particular illustration probably not so much. So let's go back to my notes and let's think about a couple of materials that are not entirely smooth, but are kind of sort of somewhat smooth. And they're resting on top of each other. Did I set this up in the way that this will work? I hope so. There we go. All right. Let's put those kind of this way so that it makes a little bit more sense. But you can see as I try to move these things against each other, this blue one is kind of settling down there where it meshes nicely. And so that's going to cause a lot of resistance. It's going to take a good bit of effort to get it up and over that. But if I've got it moving, then it's not really going to have enough time to settle back down into that before the next peak comes across. So when an object is moving, there is going to be less friction than when an object is standing still. And why is my scroll not working? I don't know. There we go. When we have the object moving, we're going to refer to that as kinetic. Friction. Right? Kinetic is the technical term for stuff is moving. And then when the object is sitting still, we're going to refer to that as static friction. Right? Static is the technical term for what we would probably call stationary, more likely. And coming back to that first simulation, again with the friction set relatively high here, what I want you to notice is watch the arrows as I start to apply force. The force that I am applying and the friction force are growing at about the same rate. And in fact, they're growing at exactly the same rate because these two forces are canceling each other out and the object is remaining in equilibrium. But if I let this go for a while, pay attention to the size of that arrow for the friction force. I will eventually hit this point where the applied force is just going to keep growing because I keep saying push it farther, push it harder, put more effort into trying to push this crate. And eventually I'm going to overcome friction. And when I do, the friction force suddenly drops. It looks like somewhere around 250 newtons in this case is when that happened. Now, one thing that can make friction a little bit more challenging is if we add extra weight. If I have to push something heavier, the weight pushing it down is going to grind those two surfaces into each other, which is going to increase the frictional force. So here you can see I'm still pushing with that same 250 newtons of force, but it has caused the crate to slow down and stop now that there's that additional mass sitting on top of it. And so I have to push harder in order to get the stack of 2 crates to move. And in fact, this is just heavy enough that I can't get it, but let's decrease the amount of friction. You can kind of see that the grass is shrinking, so we've cut the grass so we have a little bit less friction to deal with. And there we go. Now we've got these things moving. The last thing that I want to point out, I'm going to continue pushing with a little bit of force, but not a lot. Notice that the frictional force is relatively large, but then it shrinks and eventually goes away. Because the frictional force can only exist when there is motion. Kinetic friction exists whenever there is motion. When there is no motion, there is no kinetic friction. Static friction exists to counteract an applied force. The static friction can never be larger than the applied force. So if you increase the force, the static friction might increase. And that makes calculations a little bit challenging sometimes, because what we're going to calculate is not the actual static friction, it's the maximum static friction. Understanding that we are in static friction can really make a difference in a lot of situations. So whenever you're thinking about forces, you have to think about the fact that when the object is moving, there is always friction. When the object is sitting still, there may or may not be friction, depending on how many other forces are in play. All right, let's get back to my notes one last time. And finally, let's take a look at how to deal with friction mathematically. We're going to need a quantity called the coefficient of friction. Traditionally, the Greek letter mu, the same thing we use as the prefix in SI units for micro, is used as our coefficient of friction. If you want to be more technically correct, we can separately look at a mu sub s for static friction and a mu sub k for kinetic friction. I'm usually going to be lazy and I'm just going to call it mu, and I'm going to use words to make sure that it's clear whether I'm dealing with static friction or kinetic friction at the particular time. The equation as a scalar says that the force of friction is equal to this coefficient of friction multiplied by the normal force. Remember that the normal force is the force that opposes an object trying to fall through a surface. So let's draw those arrows in a different color. But if I have a box sitting here on an inclined plane, I might have gravity pulling downward. I have a normal force that is perpendicular or normal to the surface. And these forces together would give me a net force trying to go down the plane. I know that that's not what's going to really happen, because there's probably also a force of friction causing it to not fall down the plane, and then we can have a box resting on a slanted surface without any real issues. Very important to me because I am currently writing all of these notes on a touchscreen monitor that is sitting on a sloped desk, so that it's a little bit more comfortable for me to actually write these things out. If there were no friction, this monitor would be on my feet and probably in pieces. So let's take a look at the simpler case because it's a lot easier to deal with this if we have our box sitting on a level surface. Let's give that box some mass, and then let's put a person here who is applying some force. Then let's gain some information about the situation. In this particular case, I claim that it takes 315 newtons of applied force to just get the 15 kilogram block to overcome static friction. And I'm going to ask the question, what is the coefficient of friction in this case? If I sketch out a free body diagram for this block, I have 4 forces. The force of gravity is equal to mass times gravitational acceleration. The applied force is equal to 315 newtons. There is going to be a normal force, and there is going to be a force of friction. And of course, the force of friction is equal to mu times the normal force. And when I think about the directions, I guess it makes sense to call the force of friction and the force of gravity negative values. So let's put some negatives on there. Depending on how you want to set up your axes, those could be positive or negative. Some textbooks really push you should know these formulas as having negatives. I really emphasize you should draw a free body diagram and try to figure out what it's going to be. And the last thing before I scroll down, I should have highlighted this. The last thing here is that this applied force allows us to just overcome static friction. So to within a reasonable approximation, we can say that these forces are in equilibrium. And as soon as we know that these forces are in equilibrium, that gives us some nice equations. I said that this was probably the easiest setup that we could think about with friction because everything is at right angles to each other. The net force in the x direction is the applied force and the friction force. So that gives us that the applied force, or let's put it the other way, the friction force is equal to the negative of the applied force. We can get rid of those negatives. And we have that the coefficient of friction times the normal force is equal to 315 newtons. We also have the net force in the y direction. In this case, that is the normal force and the force of gravity. That also has to be equal to 0 because this object is not flying into the air nor sinking into the ground. I don't know what the normal force is. I know that Fg is minus mass times gravitational acceleration, and I can move that over to the other side of the equation. I should have done that in 2 steps. I'm talking faster than I can write. There we go. Those two negatives cancel each other out, and in magnitude, the normal force is equal to mass times gravitational acceleration. That will be true whenever you're dealing with an object that is on flat ground. As soon as the object is at an angle, or there are other forces acting at angles, that will stop being the case. Right, but if I scroll back up, I am also given that the mass is 15 kilograms. And of course, gravitational acceleration is 9.80 meters per square second. And if I multiply 15 kilograms times 9.8 meters per square second, I get that the normal force in this case is 147 newtons. Now we're getting somewhere. If I take this normal force and I plug it back in over here, I have that mu times 147 newtons is equal to 315 newtons, which means that mu itself is 315 newtons divided by 147 newtons. And my calculator is happy to tell me that if I take 315 divided by 147 and round it to 3 significant figures, I get that mu is 2.14. A couple of small things before I move on from this problem. First of all, notice that the units cancel each other out here. Right? You have newtons in the numerator, you have newtons in the denominator that cancel each other out. The coefficient of friction is a unitless quantity. That will always be the case. The other thing that I want to mention is that 2.14 is huge for a coefficient of friction. You don't usually see coefficients of friction that are that high. It's certainly possible, it's just not common. Most of the time when we're dealing with coefficients of friction, we're going to be dealing with things in the 0.5 to 1.1 range. So with that idea in mind, let's get my head back out of the way, get a little bit more space to work here, and let's take a look at one other problem. Excuse me. A 7.3 kilogram box is sliding across ice where the coefficient of friction is mu equals 0.125. As ice goes, that's a fairly high coefficient of friction, but boxes aren't exactly known for their ability to slide easily. I'm asking the wrong question. Let's go back. I could have asked how long it will take, but my notes are asking me how far will it travel before coming to a stop? Right. How long will it take for that to happen is another interesting question, but it's not the one that I wanted to solve in this video. All right, this is a challenging problem because there's a couple of things going on. I'm going to be a little bit more careful in setting things up on this problem than I was on the last one because there's a lot more steps. All right, but we have a mass of 7.30 kilograms. We have a coefficient of friction of 0.125. Coefficients of friction are unitless quantities. And we have originally moving. That sounds like an initial speed to me. V naught equals 12.0 meters per second. And then how far will it travel before coming to a stop? So our unknown in this case is going to be S. And with that, we can start to get to work. Kind of thinking through how we're going to solve this problem is in and of itself a tricky thing. We don't really have any formulas that involve both force and distance. So we're going to have to deal with something a little bit different. The tool we've used in the past for figuring out distances, S equals V naught T plus 1/2 A T squared. If we had a time, this would be a great formula to use. We don't have a time, so we probably don't want this formula either. The other formula of kinematics that involves distance is Vf squared equals V naught squared plus 2AS. I can rearrange this equation and write it as S equals Vf squared minus V naught squared all over 2A. And if we know what Vf is, if we know what V naught is, and we know what A is, then we are in good shape. We didn't write it down, but we do know what Vf is. The problem asks us how long is it going to take before the box comes to a stop, or how far will it go before the box comes to a stop. Coming to a stop means that the final velocity is going to be 0. So that's something we have. But we also need to know what A is. And we do not have A from what we've written down so far. Although I guess we have some ideas related to forces, and by Newton's second law, F equals ma, which means that A is equal to F divided by m. We have m. If we had the net force, we'd be able to use that formula and figure out the acceleration. Can we figure out the net force? Well, as soon as I realize that I have to figure out a net force, I'm drawing a free body diagram. In this particular case, let's assume that we are moving in this direction. And so we're going to have a normal force causing us to not fall through the ice. We're going to have force of gravity trying to get us to fall through the ice. And we're going to have a force of friction, which is trying to get us to stop. Our box is not falling through the ice. It is also not floating up into the air. The only way that that can work is if the normal force is equal to the force of gravity. Force of gravity, of course, is always mass times gravitational acceleration. Our mass is given to us. Gravitational acceleration is still 9.80 meters per square second. Sorry, I'm running out of space there on the edge of the screen. But grabbing out my calculator, punching that in, I get that the normal force is going to be, looks like 71.5 newtons. I still need some of these values that I have calculated, so I'm running out of space, and I don't want to keep jumping up and down, so I'm going to go ahead and copy all of that. And let's get down here where I have a clean sheet to work with. Let's paste all that stuff, put it over here off to the side where we can work around it. If I was working on paper, I would not rewrite any of this, but I would still be able to see it. I wouldn't be scrolling it off of the screen if I was working on paper. We have our normal force. Our net force is just going to be the force of friction, right? Gravity and the normal force are canceling each other out. Friction is trying to slow us down. Friction is the only thing that's not canceled out. So our net force is just the frictional force. The formula for a frictional force is still coefficient of friction times the normal force. Our coefficient of friction was given to us as 0.125. Our normal force was given to us, or we just calculated, as 71.5. And if I multiply those things, I get 8.94. Right. So our net force is 8.94 newtons. We wanted net force because the acceleration is net force divided by mass. See, our mass was 7.30 kilograms. And when I divide 8.94 divided by 7.30, I get something in the ballpark of 1.23, it looks like, 1.22. Newtons divided by kilograms, that'll give me meters per square second. Right? There's my acceleration. Acceleration is in the negative direction, so I guess I should have thought about negatives throughout all of this. Our force of friction is in the negative x direction, so these should all be negative, which means that this should be negative, which means that our acceleration should be negative. The important thing is that it's in the opposite direction of our motion, right? So V naught positive, A negative. We have to make sure that they have opposite signs of each other because we are slowing down. We're opposing motion. All right. But that leaves us with that equation of kinematics that we wrote down earlier. S equals Vf squared minus V naught squared all over 2A. Vf is 0. V naught is 12. And A is negative 1.22. You probably don't need that intermediate step. You could have punched all this into a calculator in one go. But I wanted to write it down just to emphasize, first of all, what's happening with units. Meters per second squared is meters squared per second squared. And when we take square meter per square second and divide by meter per square second, one of the meters will cancel out, both of the seconds will cancel out. We'll be left with meters, which is exactly what makes sense. I also wanted to point out that we have a negative divided by a negative, which is going to give us a positive, and that makes sense. Our box is going to be moving in the positive direction, so we should expect the displacement to be positive. But if I take 144 divided by 2.44, I get 59.0 meters. The box is going to travel a distance of 59 meters before it comes to a stop. Right, 59 meters is something in the 60 to 65 feet range. If you are better at visualizing things with US customary units, which kind of makes sense. If you have ever chased a box across a frozen sidewalk, it'll go a while. All right. I think with that, we've hit all of the hard things that we're going to be doing in this course. Of course, there are so many things we could do to make this more challenging by adding angles into things and worrying about that. For the sake of time, I'm not going to do any of that. But finding the coefficient of friction is somewhat challenging on its own. It's also a very common, necessary task in industry. And then a reminder that if we're looking for forces, we can use those to find accelerations. And once we have accelerations, we can go back and do all of the kinematic stuff that we have done before. It never goes away. Right, with that, I think I have gone on for more than long enough on this video. I'll wrap up here. Thanks as always for joining me. I'll see you next time.